Good morning to all of you. Now, after discussing about the magnetic effect of the current part first, in which we have been completed, what is the effect of the current carrying conductor and how it will produce the magnetic field. Now, we will discuss what is the magnetic effect of a moving charge. If a moving charge particle is moving in a magnetic field, then what should be the result upon it. Before studying that particular topic, I want to introduce you what are the different points topic given here. Point wise, number 1 we will discuss Lorentz magnetic force. Number 2 we will discuss Fleming left hand rule. It was also discussed at the class 10th. And third one we will discuss force on a moving charge in a uniform electric and magnetic field. If a charge particle is moving in electric field as well as magnetic field both, then what should be the effect on it. And next point, fourth is here, force on a current carrying conductor in a uniform magnetic field. If a current carrying conductor is placed in a uniform magnetic field, how it will behave. Okay. And next and fifth part is the force between the two infinity long parallel current carrying conductors. It was also given in the class 10th standard, you know very well, but here it is given in the described manner. And what is the definition of the ampere? It is the basic unit, you know very well, of current, fundamental unit of the current, and 1 ampere is also defined in the class 11th, you know very well what is 1 ampere. Next we will discuss representation of the field due to the parallel conductor and torque experienced by a current carrying coil in a uniform magnetic field. And next one, based upon that particular principle, it is moving coil galvanometer. It is a particular device which can detect the current, and after then we will discuss conversion of the galvanometer into ammeter as well as the voltmeter. And last one is here, what is the difference between the ammeter and voltmeter. All these points are very important and it is very easy to understand here. First of all, we will discuss Lorentz magnetic force. And what is it? Please see on the board, you know very well, if a particular charge, positive charge is placed here, it is a plus q, and magnetic field is directed along to the x axis, suppose it is a x axis and it is the y axis. So, you know very well, velocity of the charge particle v is directed at an angle theta and it is given here. Then what should be the direction of the force? It will always be directed, magnetic force will be directed along to the y axis. How? According to Fleming's left hand rule, when you will place your first finger as well as the middle finger along to the magnetic field and the velocity there, then your thumb must be pointed along the direction of the force. It is given here Lorentz magnetic force. When a charge small q moves with a velocity v vector in a magnetic field capital B vector at angle theta, it experiences a force which is also vector quantity such that force is directly proportional to the magnetic field, force is directly proportional to charge, force is directly proportional to the sign component of the velocity, as well as you can say after combination of all these three, force is directly proportional to qvb sin theta. Therefore, F equals to qvb sin theta. How it can be possible? Suppose proportionality sign will remove here, it becomes k q v b and sin theta. Experimentally it was observed that, by experiment it is observed that k was 1 for all the system of unit, for all the system of unit. Okay. So, therefore, when you will put the value of k 1 here, it will give the result finally like that. Now, suppose charge q is given here and that particular charge is moving with the velocity v along to that particular angle theta, it is also known as the current, you can say. Therefore, magnetic field is here and force is here. So, what should be the result? You know, vectorally we can say force, magnetic force, vector form of it will be given as the qvb sin theta. Experimentally it is observed that, and direction of the vector is perpendicular on the plane, it will be the normal n cap. Therefore, you know very well that particular force is given here Fm equals to q v cross b. It is a cross product of that particular two vectors v cross b, where theta is the angle between the vector b and as well as the vector capital B. Finally, if you know very well, instead of the positive charge, negative charge is placed, then what should be the direction of the force? You know, force will be revert. It will be opposite in direction. Why? Because you know very well, if a negative charge is moving in the same direction as positive charge was in the previous condition, then you can say positive charge or current will move opposite to it. And when you will place the fingers according to the same manner, then you will obtain the final result in opposite direction of the force. What are the special cases? See on the board. First one case is here. If the charge is at rest, mean to say in magnetic field charge is not moving, it is given as the V equals to 0, then force will also be 0 with the help of that particular formula here, F equals to QVB sin theta. Mean to say, you know, in the previous study, if a positive charge or negative charge was placed in electric field, then it must to be experience of force, electrostatic force. But here in magnetic field, if charge is not moving, then it will not experience any force. Okay. And finally, you will obtain the result. So, a stationary charge in a magnetic field does not experience any force. It is a special case number first. And case number 2 is given here. If theta is 0 or 180 degree, mean to say if the charge moves parallel or anti-parallel to the direction of the magnetic field, then force will also be 0 here. It will not experience any force, because you know very well sin 0 will be equals to 0 and sin 180 will also be 0. And if theta equals to 90 degree, if charge is moving perpendicular to the magnetic field, then what will happen? If the charge moves perpendicular to the magnetic field, then the force will be maximum, because you know very well in the same formula F will be maximum and its value becomes QVB if sin theta is sin 90, and you know very well it is the maximum value of the sine. Okay. Therefore, F max equals to QVB is given here, and here it is given that left hand, and according to left hand, if electric current is directed along to the that finger, this one be magnetic field V and force is along to the thumb. So, what is the Fleming's left hand rule? If the forefinger and the thumb of the left hand are stretched mutually perpendicular to each other, and the central finger point to the direction of the current, forefinger point to the direction of the magnetic field, and in this one situation, thumb will be pointed in the direction of the motion as well as the force in the current carrying conductor. Okay. It will be the direction of the force. For that particular charge particle which was placed here, it was the plus q and moving along to that particular direction with the velocity v, which will make angle theta here. It is condition. Okay. Finally, what is the tip for that particular condition? Remember the phase EMF to represent electric current, magnetic field and force in anti-clockwise direction of the fingers of the left hand. Then it must to be always directed along to the anti-clockwise direction. Current, magnetic field and force. It is known as electric current, magnetic field and force. Okay. So, finally, you can say all these things are very clear here, but force on a moving charge in a uniform magnetic field, which is known as the uniform magnetic as well as the electric field both. How we will find the result here? When a charge small q moves with a velocity small v in a region in which both electric field E and the magnetic field B both are exist here, then the Lorentz force is given as the F equals to QE vector plus QV cross B vector, or it can be written as the Q is taken common E vector plus V cross B vector. How can it be possible? See on the board. If a charged particle is given in such a manner, you know in the previous figure, suppose it was the positive charge, magnetic field is directed here B and the velocity of the charged particle is V, which will make angle theta, then you know now magnetic force is directed along to the y axis. Suppose electric field is also directed like that. It is electric field which is directed along to the minus y axis. Okay, it is minus y axis. Then positive charge will also experience electrostatic force Fe also along to the electric field. So therefore, final force F must be equal to the vector, and it becomes vector sum of the magnetic force as well as the electrostatic force. Is it clear or not? That particular formula is given here, and that particular formula will provide to you this one result. So therefore, we can say vector form of the force is equal to Q and vector E plus vector B cross B. So finally, we will get the result. Magnitude of that particular force F equals to E V B sin theta, and its unit be Newton. Now we will discuss what is the force on a current carrying conductor in a uniform magnetic field. Suppose uniform magnetic field B is given here, and a conductor is given in which length of the conductor is L, which current carrying conductor current is making a particular direction theta with respect to magnetic field. That particular angle is the theta which will make the current with the magnetic field. I am choosing here a small dl element, and inside of that particular dl element, suppose a small charge particle is electron which is moving opposite to the direction of the current, and its velocity of the motion is known as the Vd. And what should be direction of the force? It must be downward, because negatively charged particle is moving along to that particular direction. According to the Fleming left hand rule, it will be the force directed along to the downward direction. So what should be the result here? First of all, we know force experienced by each electron in the conductor is given as F equals to E Vd cross B, because it is the velocity of the electron, it is a magnetic field, and you know very well, finally we can write here E Vdb sin pi minus theta. Why pi minus theta? Because velocity is here and the magnetic field is here, and we want to find the angle between them. It will be velocity and magnetic field angle. Velocity of the electron is the Vd. So therefore, finally you can say its value becomes E Vdb sin pi minus theta equals to E Vdb sin theta. And you can say finally, small n be the number of density of the electrons, capital A be the area of cross section of the conductor, then number of electrons in the element dl is given as NaDl. How? Suppose total number of the electron in that particular dl element is number of electron per unit volume is small n multiplied by the volume of that particular dl element. So you know very well, it becomes n, and volume of that dl element is area multiplied by the length of dl conductor. So it will be the total number of the electron present inside of that particular dl element, and one electron will experience that particular amount of magnitude of the force E Vdb sin theta. Then what should be the net force? Force experienced by the electrons in dl element is given as df equals to NaDl. You know very well what is the NaDl? Total number of the electrons, and one electron will experience that such amount of the force. Therefore, it will be NeaVd dl cross B. So therefore, you know very well, I equals to NeaVd was the formula. So finally, you will get the result net force. It can be calculated with the help of that particular integration. df is calculated here. Integration of the df will provide the df integration of that particular formula, and you know finally you will obtain the result. That particular force is given here, F vector equals to I L cross B, and here it will convert it to the magnitude form of it, BIL sin theta. Between two parallel infinitely long current carrying conductor. See on the board, suppose two parallel wires are given, PQ and RS, current is moving in the same direction, I1 and I2 is the current, distance between the wire is R, and due to the wire PQ, due to the wire, that particular wire PQ, you know very well, suppose here magnetic field will be inward and that particular magnetic field is due to the wire first one, so it must be given as the B1, and second wire which is known as the RS will provide the magnetic field here, and according to right hand thumb rule, that particular magnetic field will be outwards at that point and must be known as the B2 vector. So what should be the final value of it? Just see on the board, you know very well B2 is here, and you know very well with the help of Fleming's left hand rule, force on the first wire is the F12 and force on the second wire is F21, both must be directed towards each other, mean to say it will be attractive in nature. Then how we will find the magnetic field on RS due to the current in PQ is given as, you know, it must be B1 equals to mu naught upon 4 pi 2 I1 by R. It is the magnitude of the magnetic field here, and you know force acting on the RS. Here that particular wire is the RS, and in that particular wire RS we want to find the force acting through the current I2 through it, because that particular wire RS is placed in which current is flowing I2 is placed in the magnetic field of the wire 1. So therefore force F equals to BIL sin theta, you know very well, F equals to BIL sin theta was the formula. So therefore B is given here, I is the current flowing in it, L is the length of that particular conductor, and you know very well magnetic field and current will make angle 90 degree here. So therefore finally we will get the result F12 equals to, you know very well, F12 is equals to mu naught upon 4 pi 2 I1 I2 L by R. B1 act perpendicular and into the plane of the diagram by right hand thumb rule. So the angle between current and the magnetic field is 90 degree and L is the length of the conductor. So therefore you will find the result. Magnetic field on the wire PQ due to the current RS is given here, B2 equals to mu naught upon 4 pi 2 I2 by R in magnitude, and force acting on that particular current carrying conductor is given here. You know very well that particular conductor is the PQ, magnetic field on PQ. That particular magnetic field is due to this one wire, and finally you will find the result B2 equals to mu naught upon 4 pi 2 I2 by R. This one wire PQ is situated in the magnetic field of this one particular wire. So therefore force acting on the wire PQ due to the current I1 through it is given with the help of that particular formula. Finally we will get the result of the force on wire first. It is a wire first and it is a wire second, suppose that. So therefore force on the wire first is given as the mu naught upon 4 pi 2 I1 I2 L by R, and here force on the second wire F on 2 due to 1 was also similar here. These two formulas are similar, therefore you can say force on these two wire is given as the F12 and F21 equals to F mu naught upon 4 pi 2 I1 I2 L by R. Here it is a force experienced by the whole of the wire. Therefore we want to find the force per unit length of the conductor is given here. Force per unit length equals to mu naught upon 4 pi 2 I1 I2 by R, and its unit will be Newton per meter. Okay, and finally now we will find the result in which if two different wires are placed in such a manner, current is flowing in the same direction, then force be attractive. And in the second scenario, you know very well, if wire is given in such a manner, current is flowing opposite to each other, then force according to the Fleming left hand rule, that particular force will be repulsive. And you know very well, by Fleming's left hand rule, the conductors experience a force towards each other and hence attract to each other. And second situation arises here, by Fleming's left hand rule, the conductors experience force away from each other and hence they will repel each other. Here in the both conditions you know very well, current is similar. Here due to that particular current I1, magnetic field will be inwards. Here due to that particular current I2, magnetic field will be outwards. But here in this one situation, due to that particular current I1, magnetic field was inwards in the like a previous condition, like here. But due to the current in opposite direction, here magnetic field, when you will place the thumb, right hand thumb along to the direction of the current, your finger must be curved in that particular wire along to the inwards direction also. Here magnetic field is inward here, but here it was outward. So when you will place the left hand and curl your finger perpendicular to each other, in that particular scenario, this one force will be opposite to that one force. Mean to say, you can conclude here, if current is in the same direction, if current is in the same direction, then force be attractive, and if current in the opposite direction, then force will be the repulsive. You can learn all that particular concept with the help of that particular only a single statement. Okay.